As we have seen in the first video, with the theory of special relativity, Einstein thus solved the first problem. What about the second one? How can it be possible that two objects at a distance can influence each other instantaneously through gravity? The answer to this question is that it is indeed impossible, as shown by the theory of general relativity, formulated in 1915. Let us try to understand some basic ideas behind it. The most important concept is that gravity ceases to be a force in the Newtonian sense. All objects with a mass, or energy, have the effect of curving the framework in which they exist, that is, the four-dimensional space-time. And the higher their mass, or energy, the higher the induced curvature. It is this induced curvature in the nearby space-time regions that makes the other bodies follow curved trajectories in space. As John Archibald Wheeler once said, space-time tells matter how to move, and matter tells space-time how to curve. In a curved space, the shortest path between 2 points is known as geodesic line, and in general, it is not a straight line. For example, for the curved surface of a sphere, such a line is shown here. Well, in general relativity, objects affected only by gravity follow geodesic lines in the four-dimensional space-time. The projection of such lines into the three-dimensional space is what we call the gravitational trajectory. In order to have an intuitive idea of how this works, consider the trajectory of a small ball in a rubber sheet with a much more massive ball in the center. This ball curves the rubber sheet in such a way that the small ball will deviate from a straight trajectory when approaching the big one. The obvious explanation is that the small ball tends to deviate because of the local slope of the rubber sheet, but imagine what we would think if we could observe the motion from the top. Although the real trajectory is three-dimensional, we would observe a 2D curved trajectory, and we would be induced to believe that its bending is due to some horizontal gravity force, whose origin would be mysterious. Well, the fact that we live and think in a three-dimensional world, in which time and space are two well-separated concepts, is what led us to believe in the existence of the Newtonian gravity force. Einstein, by broadening the perspective to 4 dimensions, proved that Newtonian gravity is only a fictitious force that disappears in a space-time description of the world. But please don't feel upset by this, because all you have learned in this course is still very useful. It turns out, in fact, that Newtonian gravity represents a very good approximation for the prediction of gravitational trajectories, and that the effects of general and special relativity can be included by adding some perturbation terms on the right-hand side of Newton's equation, in the so-called post-Newtonian equations, the most accurate description of gravitational motion existing to date. Returning to the initial question, in general relativity, gravity is no more a means of transmitting information instantaneously. When a massive body moves or accelerates very quickly, the space-time curvature adapts to its new position by means of space-time ripples propagating at the speed of light. So, if the sun should suddenly explode or disappear now, we would not feel it gravitationally for at least 8 minutes. That is the time it takes light to cover the distance between the sun and the Earth. These space-time ripples, responsible of the changes of the local curvature in space-time, are known as gravitational waves and are an essential ingredient predicted by the theory of general relativity. As you might know, gravitational waves have been recently detected for the first time by the LIGO experiment. And in the future, a space mission will try to improve the quality of such measurements It's the European Space Agency's LISA Pathfinder mission. Such mission, whose concept is the same as that of the LIGO experiment, but at a much larger scale, will place 3 spacecrafts in space at very large distances between one another, and will measure the variation of the distances between 2 pairs of satellites with laser interferometry. An incoming gravitational wave should have the effect of stretching one distance and shrinking the other at the same time. If such an ambitious mission had success, it could pave the way to a new type of astronomy based on the detection of gravitational waves. Another great consequence of the general relativity theory is that everything is subject to gravity, even particles with a zero rest mass, like photons. Because gravity means following the geometry of spacetime, and everything must do that. With equations of general relativity, Karl Schwarzschild predicted in 1916 the existence of black holes, in which the extremely high density of matter makes space-time curve so much that not even light can escape. As you might know, our universe has plenty of these black holes, and there is a huge one at the center of our galaxy. Their discovery was, once again, a gift of this revolutionary theory. Now, you might wonder how Einstein ever started to conceive something like this. How could he have ever conceived that gravity was only the effect of the geometry of a 4-dimensional spacetime? Well, he had a great physical insight. Do you remember the falling elevator you met with Mario when studying microgravity in week 3? In a falling elevator, everything looks floating and at quiet with respect to the walls. So, if we freely follow the curvature of spacetime, like a falling elevator does, we feel weightless, just as if we were in an inertial reference frame far from any gravitational field. The fact that a freely falling reference frame is equivalent to a quiet, non-accelerating reference frame away from any gravity source is what led Einstein to think that gravity was not a real force. When the elevator is hanging, on the other hand, we feel the reaction force on the floor that accelerates us away from our inertial motion in spacetime, which would be falling. The same situation occurs in an accelerating reference frame, like an accelerating spaceship, firing its rocket in empty space. So from a physical point of view, the effects of gravity and those of an acceleration cannot be distinguished. This is the principle of equivalence, the major postulate of the theory of general relativity. Let's now see one of its most direct consequences. Imagine an upwards accelerating spaceship with 2 astronauts, one at the top and one at the bottom of the spaceship. Suppose that the top astronaut sends pulses of light at a constant rate with the help of a clock. At the same time, the bottom astronaut measures the time between the receptions of such light pulses. Since the spaceship is accelerating upwards, an outside observer will see that the bottom astronaut measures a shorter time between the pulses than the top one, simply because he is accelerating towards them. For consistency, the observers inside the spaceship must observe the same. The bottom astronaut measures a shorter time with his clock. And here comes the principle of equivalence. The astronauts inside the spaceship cannot be able to tell whether they are accelerating or standing still inside a gravitational field. If they decide to think that there is a gravity field towards the bottom of the spaceship, the only explanation they can give is that time flows slower as they get closer to the bottom floor of the spaceship, along this gravity field. And indeed, in general relativity, time runs slower and slower as we move along the local gravitational field. And the farther away we go, the higher this effect. This phenomenon is known as gravitational time dilation, and its effect has already been measured and verified in satellites orbiting the Earth. Let us consider, for example, the case of the GPS satellites that you have already seen last week. orbiting at an altitude of 20,000 kilometers. Since they are orbiting at 3.87 kilometers per second, special relativity predicts a time dilation factor slightly bigger than 1, meaning that their time should flow slightly more slowly than for an observer at rest on the Earth. If we do the math, we find that such a time dilation should be 8 microseconds per day. However, GPS satellites are also 20,000 kilometers away in a direction opposite to the Earth's gravity field, so that their time should run quicker by some factor. It turns out that this translates into approximately 46 microseconds per day. So, in total, a GPS satellite clock runs ahead of ours by approximately 38 microseconds per day. This is not a big amount of time, but big enough to be easily measured with atomic clocks. And since the precision requirements for GPS clocks are very stringent, such clocks have to be systematically corrected in order to maintain their synchronicity with the Earth.